Alrighty. Good evening, everyone. Welcome to our CASI Ottawa branch event this evening. We have a very special guest, Professor Emeritus Herb Saravanamuttoo, who will be giving an updated presentation on civil propulsion, originally entitled The Last 50 Years. It's been updated to cover the last 20. It is really our honor and privilege, CASI Ottawa branch, Jeff Bird and myself and CASI HQ, to welcome Professor Emeritus Saravanamuttoo and all of you to this Zoom event. I will start with a biography to introduce our esteemed speaker. So Professor Emeritus Herb Saravanamuttoo was educated at Allen Glen School, Glasgow, and the University of Glasgow. After graduation in 1955, he joined Arenda Engines in Canada, where he worked on the development of the Iroquois engine for the Aero and a family of aeroderivative gas turbines. In 1964, he became a faculty member at the University of Bristol, where he worked with Bristol Siddeley, later Rolls-Royce, and British Aircraft Corporation on the development of the Olympus 593 and Concorde. And he also worked with Rolls-Royce on early development of the legendary RB211 turbofan engine. He obtained his PhD in 1968, and he joined Carleton University in 1970. He spent 28 years there, including 10 years as chairman of the Department of Mechanical and Aerospace Engineering. And he retired for the first time in 1998, and actually then again in 2018. He was founding director of Gastops, and he has maintained strong contacts with the gas turbine industry on both sides of the Atlantic. He has worked on gas turbine diagnostics for a wide range of aero and industrial gas turbines, and he continues to lecture at Carleton and Cranfield and has given many in-house courses at both gas turbine manufacturers and users. He is a fellow of ASME, IMECE, CASI, and the Canadian Academy of Engineering, and past president of CASI. He is a lead co-author of Gas Turbine Theory, now entering its 7th edition and in continuous print since 1951. He is the recipient of numerous awards, including the 2004 ASME R. Tom Sawyer Award, the 2005 CASI McCurdy Award, and the 2019 ISABE International Society of Air-Breathing Engines Lifetime Achievement Award. As all of his former students know, Herb's passion for gas turbines and teaching is unrelenting and incredibly inspiring. He may be one of the few to have ever crossed the Atlantic on Constellation, Comet, and Concorde, possibly the only one. Finally, Herb doesn't always travel, but when he does, he prefers business class. So with that introduction, I will start the presentation and share my screen. Great. Hopefully everyone can see.
There we are.
Over to you.
Thank you very much, Omar. Good evening, everybody. It's a great pleasure for me to be here. I'd be much rather talking in person, but this is the way that the world is going. If we could just say a few words about this talk. This was actually the Guggenheim lecture I did in 2002. And at the beginning of this lecture, we added in a few extra slides, which I actually did at the 75th anniversary of Pratt & Whitney Canada. So we'll start with those and then get on to the Guggenheim. So can I have the first slide, please, Omar? Homer, first slide,
Yeah,
please.
yeah, just a moment. There's a little bit of a technical hiccup here. Just a
Oh,
moment.
that's part of the course.
Yeah. And,
There we
oh,
are.
there we go. A little bit of a delay.
Perhaps this is more interesting to the Carleton students who are at the beginning of their careers. We know, of course, the Wright brothers started at Kitty Hawk in 1903. The first big achievement was Blériot flying across the English Channel. That was a really big deal in 1909. I've been to the point where Blériot landed, and it was a very, very unflat piece of land. In 1919, we had the first non-stop Atlantic flight by Alcock and Brown from St. John's, Newfoundland. Newfoundland was very important in the early development of aviation because of its proximity geographically to Europe. The first solo Atlantic flight was by Lindbergh, 1927, and 1932, the first women's flight was done by Amelia Earhart. Next slide, please. Okay, now it's interesting that before the war, when they were starting to look at transatlantic flights, the whole idea was going to be flying boats. There were no long runways, and Pan Am had the Boeing 314 Clipper. Imperial Airways in Britain had the short C-class flying boat, which eventually became converted into the Sunderland. But you see that with the Boeing 314, the flight path was New York to the Azores, to Lisbon, to Marseille, and in fact to Southampton, and then the boat train to London. So it was 4 or 5 stops. The Imperial Airways flight went New York, Montreal, and if there's anybody from Newfoundland, Botwood was going to be a major centre of the flying boat world, and then Foynes in Ireland and to London, again to Southampton. Now, some years ago, in fact, I made a special trip to have a look at Botwood, and there is absolutely nothing there because, of course, the flying boats have all disappeared. Now, of course, the thing was the flying boats, they had a maximum speed of about 150 miles an hour, but they cruised at about 120 miles an hour. And if you hit a 50-knot headwind, you didn't make much speed across the water. And in fact, before the war, one of the C-class flying boats flew from Foynes to Botwood in 19 hours. And some days they couldn't make it if the headwinds were too high. Now in 19 hours, we can get from Singapore to New York non-stop. Next slide, please. Okay, the first flight scheduled across the transatlantic was DC-4. Of course, DC-4 was unpressurized and flew at 10,000 feet. Don't know how many stops they had to make. But the Constellation, the Lockheed Constellation in 1946, was able to do it eastbound in just over 14 hours. Now, they could do it non-stop eastbound with the wind behind them, but going westbound required 1 or 2 stops. In fact, when KLM were flying Constellations from Amsterdam to New York, they had to make 2 stops, one at Shannon and one at Gander, and it was a very long trip. Next slide, please. The first jet flight came in 51 when a Royal Air Force Canberra bomber flew from North America from Northern Ireland to Gander, which is just over 2,000 miles, and they actually did a return trip in the day. In 1954, Mike Collins, the Apollo 11 astronaut, the command module pilot, led a fleet of F-86s from US to France. And because of weather and the short distances where they had to stop, it took them 30 days, and he actually worked out that the average speed for the trip was 4 miles per hour, which is not terribly good. In 1958, on October the 4th, BOAC very smartly started the transatlantic flight with the Comet 4, a very smart piece of marketing because Pan American had announced they were going to start the flights on October 27th with the 707. When British Airways heard, BOAC heard that Pan Am at this date planted, they promptly put a Comet at each end and were always able to claim afterwards they were the first across the Atlantic. But October 27th, of 1958, that was the beginning of the real jet age. Next slide, please, Omar. Okay, so here's the progress from 1903. It took 16 years from the first flight to get to a transatlantic flight, 24 years before it could do a long flight like New York to Paris, 43 years to schedule the transatlantic flights, 55 years to schedule jets, 65 years to the first flight of the Concorde, 67 years till the 747 came in, brought in the wide body age, 100 years to the end of the supersonic era, and Concorde stopped flying in 2003. In 112 years after the start, we got the first 330 minutes ETOPS flight with the Boeing 777-200ER with Rolls-Royce Trent engines. So that was the progress it took. In the first 100 years, we went from the beginning of powered flight to the end of the supersonic era. And there are currently some projects floating about for supersonic aircraft, which might or might not come. But the Concorde did in fact fly for about 25 years at supersonic speeds. Okay, next slide, please. Okay, now this is the outline of the lecture as I gave it first, 2002. So we look back 50 years to 1952, which was just about the time I started. My very first gas turbine job was in 1953, testing turbo starters on the Armstrong-Siddeley Python turboprop. So the 1950s was the era where we changed from pistons to turbines. 1960s was turbojets. 1970s, the entrance of the high bypass turbofan. 1980s, the entrance of the big twins. 1990s, the regional market growing up. 2000s, we went back to high fuel costs. 2020s, we got the COVID pandemic, which has totally changed things. Now, so in fact, the Carleton students who are here, most of you would be born round about 1998, 2000 or thereabouts. And the 777 came into service in the late 1990s. So not much has changed since you were born. But we'll talk a little bit more about that. Next slide, please, Omar. If you go back to 1952, every crossing the Atlantic, nearly every went by ship. The air market, there was a small domestic US market, very small transatlantic, and negligible, I think in fact zero, trans-Pacific. And of course, rail was transcontinental and local. Now, I came to Canada in 1955, and nobody would have thought then of making a day trip from Toronto to Montreal or Toronto to Ottawa. That was an overnight trip by train. Next slide, please. There was no leisure travel in the 1950s except for the mega rich, and there was no business travel. What drove travel in the 1950s was large-scale immigration. At the end of the war, there was very large-scale immigration from war-torn Europe to North America, to the States, to Canada, to South Africa, to Australia, to New Zealand. And that was all done by boat. Immigrants didn't come by aeroplane. One of the common expressions of denigration about immigrants is, oh, he's just off the boat. And that I was one of those too. So next slide, please. If you look at ships, a typical London-Montreal trip was 8 to 10 days, London to Colombo, 18 to 21 days, London to Sydney, 30 to 40 days. And a typical cruise speed of the average ocean liner was in fact 18 to 20 knots. One of the disadvantages of ship travel was that where aeroplanes can essentially follow
I'm going to ask you to stop. We seem to be having a bit of a transmission problem here. We seem to be having a bit of a technical issue with Dr. Saravanamuttoo's connection. We're going to try and get him back here momentarily. Hopefully it's just a case of he just needs to give it a little bit of a rest and he can just get it back going again and should be okay. Please be patient.
Okay. Okay.
It seems okay now.
Are we okay now?
Seems okay. Thank you.
Next slide, please, then. Okay. Now, the Canard line in the UK had, before the war, planned the express liner two-ship operation where you could do London to New York in about 4.5 days. And so one ship would leave New York on a Saturday and the other ship would leave London, that is Southampton, and they would restock at each end. And the typical cruise is not quite right there. Typical cruise was 28 knots. That was what it was designed for. But the Queen Mary was in fact capable of 30 knots and did in fact get the Blue Ribbon across the Atlantic at just over 30 knots. But the basic design speed, the whole operation worked around this 28 knot service speed. Now these ships carried over 2,000 passengers, but they also carried a crew of about 2,000. Now when people talk about fuel efficiency, I did a kind of back of the envelope calculation on this and came to the conclusion that we burned about 4,000 pounds of fuel per passenger for the transatlantic crossing. The magic number I came across when I actually visited the Queen Mary in Los Angeles was the Queen Mary did 10 feet to the gallon. So that's a number, it's easy to remember. But those were very successful, but they did use a very large amount of fuel. So the next slide, please. Now, I want to talk a bit here about long-range flights, and I'll get into the pistons and then the turbojets, turbofans. But as far back as 1989, we actually did non-stop flight from London to Sydney, 9,820 nautical miles, RB211-524G. 1993, Auckland to Paris, 10,392 nautical miles, CFM 56-5C. 1996, Seattle to Kuala Lumpur, 10,823 nautical miles, Rolls-Royce Trent. 2005, Hong Kong to London, 11,664 nautical miles. Now, being an engine guy, I put that up to annoy the aeroplane people. Of course, these were in fact connected to different aeroplanes. We'll see that in a minute. But the interesting thing is, if you look at the numbers there, if you go back to the original definition of the nautical mile, 1 minute of arc at the Earth's circumference, you find that actually the maximum distance halfway around the world is exactly 10,800 nautical miles. Now, in fact, the Seattle to Kuala Lumpur, 10,823 nautical miles, they obtained that distance by going the wrong way. Instead of going across the Pacific, they went across the Atlantic. And similarly, with the long flight from Hong Kong to London, again, they went the opposite way to establish these very long. So these were the actual longest flights made up to that time. Now, the first flight, put up the next slide, please, Elmer. The first one was in fact done with the first delivery of a Qantas 747-400. It carried six passengers. Go back to, where are we? Oops. Go back to that slide, please. There we are. It carried six passengers. It carried the president of Qantas and his wife, the president of Boeing and his wife, president of Rolls-Royce and his wife, and their luggage went on another aeroplane. They loaded the aeroplane with special high-density fuel. They towed it to the end of the active runway, and they were still climbing when they got to Perth, Australia. They landed with virtually empty tanks. In 1993, at the Paris Air Show, Airbus flew an A340 non-stop from Paris to Auckland and back, right around the world with one stop. And then they raised the number further with Malaysian Airlines, with one of the first 777. And then finally, the distance that's never been exceeded still with the GE 9115 in the 777-200 LR. So we basically are around in the situation now where we can go halfway around the world without stopping. And we'll come back to that a bit later. Next slide, please. Okay, now I want to show you how the whole air transport business and the civil propulsion business has changed over the last 50 years, 70 years actually. In the 1950s, the major aircraft manufacturers were Lockheed and Douglas. The short-haul aircraft manufacturers were Martin, Convair, and Douglas. Let's look at the next slide. Next slide, please. The engine manufacturers were Pratt & Whitney and Wright. Next slide again, please. The dominant airlines were Pan Am and Trans World Airlines. The dominant aircraft were the Lockheed Constellation and the Douglas DC-7. Now, if you look back at these last three slides, things have changed a lot. Probably most of these young people have never heard of Convair or Martin, except we now know of Lockheed Martin. Wright is not in the business anymore. Lockheed is out of the business. Douglas is out of the business. Pan Am and TWA, both bankrupt. You notice he didn't mention a few names like Boeing, Rolls-Royce, General Electric, and Airbus, who have now essentially become a very large part of the current market. And it boils down to the fact that companies that didn't remain competitive with their products eventually disappeared. So you have to remain very active in the research side, development to keep going. And I say all these were the household words when I started in the business. A lot of them have gone now. People like Boeing, GE, Airbus, and Rolls-Royce have appeared in the market. Next slide, please. Now, this was Air Canada. Air Canada flew with the Lockheed Constellation, which is a beautiful aeroplane. But as my first transatlantic crossing, it was well over 14 hours with a stop in Iceland. Well, my first crossing was from this end and coming back. Coming back from Glasgow to Toronto, I had the misfortune to come on a Lockheed L1049H. Those of you might recognize the H as the cargo version of the Lockheed Constellation. And quite apart from no in-flight entertainment and no back of the seat screens, also no windows. So it was an enclosed tube. You sat beside this vibrating wall for 14 hours. And I can assure you it's much, much better to fly in a modern aeroplane than it was in those days. Next slide, please. Now, these again were numbers I worked out in the back of an envelope as best as I could. But typical cruise speed of the Lockheed Constellation was about 275 knots. Difficult to handle in the number of passengers, but about 74 was the best reasonable estimate I could get. And it had a flight crew of 5. Now, it's important to realize this flight crew of 5 consists of 2 pilots, a flight engineer, a navigator, and a radio operator. That didn't count the 2 or 3 stewardesses in the back. And again, estimated fuel per passenger about 520 pounds. That's just a good estimate. But you see, that's already about 8 times better than the Queen Elizabeth, Queen Mary. And of course, in those days, nobody worried about fuel or the environment in the slightest. Next slide, please. The DC-7C and the Constellation both had the right R3350 turbo compound. We much later had that in the Argus, the CL28, 14-cylinder 2-row radial, basically about 1 horsepower per pound. Now, those engines had a maximum overhaul life of 2,500 hours. They very seldom achieved that, and it took them 17 years to get there. But the point was that they couldn't go beyond 2,500 hours. And that sounds like a pretty silly number by today's standards, but that's what was the best you could get with these piston engines. Next slide, please. STRATOCRUISER had an even worse engine, the Pratt & Whitney R4360. Those numbers, those 4-digit numbers, are in fact the cubic capacity in cubic inches. And the right 3350 was 54.9 litres. But this engine was a 28-cylinder 4-row radial. You see again about the same horsepower and weight, but again, this maximum overhaul life of 2,500 hours. Now, the interesting thing about the STRATOCRUISER was, in fact, that the Boeing built only 55 of these. It was actually based on the wing of the B-29 bomber, but Boeing made 55 of these, and 13 of these finished up as hull losses. It could carry, I think it was 61 passengers across the Atlantic eastbound and 55 westbound, again, because of the wind. And there's a very good paper where it was the chief engineer of Pratt & Whitney who said the in-flight shutdown rate in the R4360 was simply intolerable. It was too dangerous even to quote a number on it. So next slide, please. So the transition to turbines, the Constellations and the DC-7s and the few STRATOCRUISERs started to open up the market. But people began to realize that really maybe the day of the piston engine was coming to an end. So there were two camps that opened up, turboprops and turbojets. When I was a student, there was a great argument going on all the time about which was better, the turboprop, the turbojet. In fact, the answer was the turbofan. But the point was, in Britain, they came up with 2 turboprops, both quite successful. The Viscount, and in fact, Air Canada was, I believe, the biggest ever user of the Viscount. The Viscount came on the scene just before I got to Canada. They also built the Britannia, which was in fact a long-range aircraft. And it sounds incredible today, but the Britannia actually did non-stop flights from New York to Tel Aviv. Lockheed also went for turboprops, and they went with the Electra, but that was intended for internal use within Europe and North America, fairly restricted range aircraft. And it unfortunately had a sort of major flutter problem, with connectivity between the nacelles and the wing, and it was sufficiently serious problem that the wing came off when the Electra was commercial failure. Of course, the Electra became the father of the P3, and we still have the P3s flying 70 years later. They're coming to the end of their lives, their lives too. On the turbojet front, the Comet was the very first, and the Comet was actually flying. The Comet had actually been withdrawn from service before the DC-7C made its first flight. So Douglas were really quite late to the game. But anyway, Britain started off with the Comet. Well, again, perhaps back up a sec. One of the reasons that Britain wanted to get into the long haul market was that during the war, virtually all the long haul transport was done by the US with the DC-4 on the first Constellation. So the Americans had built a huge lead in the transport aircraft, and the British thought that if they could get in with the turbines first, they could capture quite a lot of the market. Boeing came along with the 707, which is of course much bigger than the Comet, and Douglas were again late to the game, but they came along with the DC-8, which was much the same as the 707. Next slide, please. Okay, if you look at the turboprops, the Viscount had the Rolls-Royce Dart, which was a two-stage centrifugal compressor. The Britannia had the Bristol Proteus, which was axi-centrifugal compressor. The Electra went the Allison 501, all axial, and the last big turboprop was the Vanguard with the Rolls-Royce Time, which was all axial. Now the Vanguard, it's interesting, there was a very good paper in the CASI journal, way back in the mid-50s by Jack Diamond, who was the chief engineer of Air Canada, about the Vanguard. And it didn't even mention propulsion as being important. Fuel was simply not important in those days. And the Time was in fact quite a big turboprop for its day, 6,000 horsepower, and it became later used a lot in naval engines as well. Next slide, please. Now this is, I'll just stop for a little bit in the Allison T56, because the T56 has quite an interesting heritage. First of all, if you look at the gearbox on the left, it can be mounted either with the propeller center line above the engine center line, and that's the installation on the Electra and the P3, or it can be the other way around with the propeller line below the center line of the engine, and that's what we have. Sorry, that's the operation in the Hercules you see there, and the other way around on the P3. If you look at the gearbox there, it's in fact an infinitely more complex piece of machinery to what Pratt & Whitney have come up with now for the geared turbofan. The other interesting thing about the T56 was the gearbox was a separate item maintenance-wise from the engine. And it was the first engine to have a remote gearbox like that. And this, in fact, originated in the Bell Airacobra P-39 World War II fighter, where the engine was mounted quite far back with a very long drive shaft forward to the propeller, with the propeller shaft running in between the pilot's legs. And the T-56 has been a remarkably successful engine. There's still lots of them around. It's been developed to higher and higher standards, and about at least 12, 15,000 built. So next slide, please. Next slide, please. Okay, this was the Vanguard. Now, the Vanguard, actually, I thought was a very nice aeroplane that I flew quite a lot in Air Canada Vanguards. But I always say that the Vanguard had a unique solution to the noise problem. They managed to put all the noise into the passenger compartment, and the aeroplane was very quiet outside and hideously noisy inside. So it was not really an ideal situation. Now, the Vanguard was fast, it was reliable, it was very safe, and they sold a grand total of 43 to Air Canada and to British European Airways. So it was actually one of the very first aircraft that was, when it was being designed, it was in fact referred to as an Airbus, something to provide cheap transport and complete flop in the market. Next slide, please. Okay, so then we leave the turboprops just now. We'll come back to it a bit later. But the transatlantic service by jet started, I said, October the 4th, 1958. There's a very important date that in 1958, the Atlantic passengers by air exceeded those by ship for the first time. And what really happened was that the ship market peaked in 1958 and disappeared rapidly, whereas the aircraft market just kept on growing and growing. And the speed and economics of the initial jets brought the cost of fares down, and it made it possible for the working stiff to go for a 2 or 3 week holiday to Europe for the first time, for the first time ever. Now, I grew up in the Clyde, which was the world center of shipbuilding. I was as interested in ships as I was in aeroplanes, and I could have never guessed that 10 years after I graduated, basically the building of passenger ships was finished. Now, we still have passenger ships, of course, but they have nothing to do with transportation. They're floating resorts. Cruise ships are just basically hotels that move around. Next slide, please. Now, if you look at the sea versus air picture, in 1958, they say that air travel exceeded those by ship. The QE2 was the last big liner built in the UK, launched in 1967. The original Queen Elizabeth withdrawn in 1968. The United States, America built a large, very fast liner called the United States, which only did about 10 years in service before it was withdrawn. And the ship traffic was basically killed by the jet engine. One of the things that killed the ship traffic was that a great deal of the market was the immigrant trade from Europe, particularly to Australia. And the Australian government found it was much more economical to rent a 707 and fill it up with people and fly them to Australia in a day and come back. And that wiped out ship traffic literally almost overnight. The Dutch, in fact, also, a lot of these ships would come back, they'd go full of immigrants one way and go back almost empty. But they did, in fact, carry a lot of cargo and the Royal Mail, which kept them going. But that traffic pretty well disappeared and was totally replaced by long-haul jets. It's interesting that the year after I was born, they opened the air route from London to Sydney, known as the Kangaroo route. And younger people find this hard to believe, but when the Kangaroo route opened in 1934, it took 42 stops to Australia and took 12 days. So that we've certainly made some progress from there. Next slide, please. Now let's look at the early jet-powered aircraft. The Comet 1 had the de Havilland Ghost, which was a centrifugal compressor engine with a low pressure ratio and not quite inefficient. The 707 had the JT3, which was in fact a civil version of the J57 military engine. The Comet 4 had the Rolls-Royce Avon, which was also started as a military engine. And the DC-8 to the JT4, which was a civil version of the J75. And of course, the J75, what was used in the prototype of the Avro Arrow. It was certainly clear that for big efficient engine, it was going to be all axial, and the centrifugal was just something to get things going. It was much earlier and quite inefficient. They did, in fact, the Comet, British Airways, or BOAC as it then was, actually did fly the Comet from London to Tokyo with 9 stops, and from London to Johannesburg with either 5 or 6 stops. So again, totally different from what we know today. Next slide, please, Homer. Now, if we look at the pressure ratio and turbulent temperatures and thrusts of these engines, they seem quite ridiculous by what we know today. Pressure ratios 10 or 12, turbine temperature 1150, 1135, 1205. Now, if you look at a modern engine, civil engine with a pressure ratio of 60, the compressor delivery temperature is about 1100 Kelvin. And the pressure ratios have gone up from 10 to 50 or 60, and thrusts have gone up to about 100 115,000 pounds, the maximum so far. Next slide, please. The problems with the turbojets were, first of all, the SFC, specific fuel consumption, which is a measure of the thermal efficiency of the engine and includes the propulsive efficiency, but also high noise problem. And the high noise, and both of these problems resulted from high jet velocity. So the solution to improve the SFC and reduce the noise was to increase the airflow and decrease the jet velocity. So basically thrust is fundamentally just the mass flow into the engine times the change in velocity. So you can either have a very large mass flow and small change in velocity, which is what the propeller is doing, or a small mass flow with a very high jet velocity, which is a straight jet engine, and the turbofan, as we know it today, is in between these and has led to these tremendous increases in performance over the years. Next slide, please. So if you look at the early turbofans, the JD3D was in fact a modification of the GT3 to put a fan at the front, and that went on to both the 707 and the DC-8. And the thrust, you see, there's gone up to 18,000 pounds. JD8D was conversion of a smaller military jet engine. Forget the J50, forget which it was, 58, I think it was. No, it wasn't 58. Never mind. But the point was the JD8D went into the 727, the DC-9, and the 737. Now, if you look at that there, 707, DC-8, 727, DC-9, 737, that is about 95% of the civil market. Pratt & Whitney owned that market. Rolls-Royce had a tiny, tiny share. GE weren't there at all. And Wright had disappeared by this stage. So Pratt & Whitney had domination of the market like nothing's ever been seen before. Next slide, please. Okay, this is the JD3D, which has got the two-stage fan and a low bypass ratio, a bypass ratio just over 1. Next slide, please. Again, the JT8D is again a very low bypass ratio, bypass ratio at 0.8, I think it was, on the JD8D. But that was, in fact, for a long time, the most widely produced engine in the world. Now, the JT8D pretty well all gone now. That there were still quite a lot of them around in the 737-200. 727's been gone for quite a few years. And what was First Air and then Air North did fly JD8D powered 737s up until quite recently, but they're pretty well all gone now. Next slide, please. So turbofans, what we wanted to do was to increase the bypass ratio to improve the SFC and lower the takeoff noise. There were a lot of problems with the design and introduction of big high bypass turbofans. You needed long fan blades. There was big problems with 3D aerodynamics. People didn't know enough about the high Mach numbers at the blade tips or the tendency of the flexible blades to untwist. Materials were a problem, particularly with bird strike resistance. And if it was not for titanium, we could have never gone to the big turbofans. If you'd made the fan blades out of aluminum, they would have been unable to withstand the bird strike. And if you'd made them out of steel, you could have never made a disc strong enough to hold the blades with the diameters needed. So we started off with the solid titanium blades with dampers halfway up, or two rows of dampers. We finally moved to wide chord blades without dampers. We went to hollow blades, and you may have heard just a week or so ago there was a fan blade failure on a 777 on a Pratt engine. But the point was that the titanium was the key to being able to go to a high bypass ratio. Many, many years later, we finished up going to composite blades, and we're still getting better at that, but they've been in service for quite a long time now. Next slide, please. Now, the large turbofans, particularly the high bypass ratio, started with the military transport program in the US, the C5A. And GE came up with the TF-39 engine with the unheard of bypass ratio of 8. Look at the next slide, please. Now, if you look at the TF-39, it's a very unusual configuration. This is what is known as a 1.5 stage fan. You see that there's 2 fan stages, and the bypass flow, some of it goes through 2 stages and then into the core, and then a fair chunk of it goes through the outer part of the fan for only 1 stage of compression. Now, if you look down at the gas generator with the large number of stages in the compressor there, in the turbine, and in the big 6-stage turbine to run the low-speed fan, that is in fact now the General Electric LM2500, which has been the most successful in aeroderivative engine ever built, and they're still building lots of these. And in the case of the naval ships, they have the 6-stage turbine with a gearbox to drive the propeller. But if you want to drive a compressor in a pipeline, you'd have a 2-stage turbine running at much higher speed, directly coupled to the compressor. But that basic architecture of the TF-39 was ideal for the C5. Now, for the C5, they wanted good short field performance, but they weren't so concerned about cruise speed, and they weren't the least bit concerned about noise. But that was unsuitable for a civil engine, and all the civil engines, for noise purposes, have to have a single-stage fan. Next slide, please. Now, the Boeing 747 was the first civil application of the high bypass turbofan. The JD9D Pratt & Whitney, bypass ratio of 5, pressure ratio 22.5, turbine inlet temperature 1470 Kelvin. And that was very hot in those days. Thrust 46,000 pounds. Next slide, please. Now, Douglas and Lockheed didn't want to get left behind on the high bypass wide body, and they in fact come up with a couple of competing tri-jets, DC-10 and the Lockheed 1011. The DC-10 went with the GE CF650, which was a bit like the TF-39 with a single-stage fan, and Rolls-Royce went with the Lockheed 1011, the RB211, and the cycle conditions pretty much the same on all of these. The big difference with the Rolls-Royce engine was they went to a 3-spool engine. Now, the interesting thing is that architecture on the GE engine and the Rolls-Royce engine has lasted for the last 50 years, more than that actually. And Rolls are just now looking at this ultrafan where they've gone to a completely new architecture. I believe GE are looking at a geared fan engine, but nothing is that. I believe they will have to be, because with the increasing bypass ratios people are going to, you eventually have to go to a gearbox because the low pressure turbine becomes so massive. So the next slide, please. Now, there were some terrible reliability issues when these first came into service. Turbine blade life was a major problem because the blade temperatures were much higher than we'd had before. They required the use of advanced cooled blades. And I know that when British Airways first introduced to the 747s, they were having to change out a high pressure turbine once a week because the blade life was so poor. And that was not a Pratt problem. That was a problem with all of them because of the high temperatures. But a particularly odd problem on the JD9D was the engine had been perfectly good, tested on test beds, but when they actually mounted it on the pylon on the 747, it in fact, when it went to full power, the casing went oval. And in fact, this meant that they had to open up all the tip clearances, and that cost Pratt & Whitney a huge amount of money to put right, because the performance of the engine lost so much from these big tip clearances. But all of the big engines to start with had reliability issues. Now I should point out, I'm not going to sort of throw boulders at any engine company, because what you find happening is that when you go to a new engine and you push the technology and you go to higher temperatures and higher pressure ratios and higher speeds, you're going to have trouble, period. Doesn't matter who you are. It's a case of how long it takes you to fix them. Okay, next slide, please. Now, nobody was very keen on the idea of going to 3-engined aircraft in the Atlantic. I actually went on a DC-10 across the Atlantic the day after it had its certificate of airworthiness restored. The DC-10 lost its C of A for quite a long time because of structural problems, with problems with the floor collapsing and interfering with control cables and whatnot. But anyway, the Lockheed 1011 and the DC-10 were initially conceived as transcontinental aeroplanes, like London to Los Angeles to New York, San Francisco to New York, that sort of thing, but not transatlantic. And nobody in the right mind would have considered twin-engined aircraft across the Atlantic. And I know for sure that when I first crossed the Atlantic in a 3-engine aeroplane, I was none too happy about it, especially that a lot of these engines were designed by guys that I taught, and they were no smarter than I was. Next slide, please. Okay, now this is interesting about reliability. As I mentioned earlier, the large piston engines had a 2,500-hour overhaul life after 17 years. But the JD4, the first big jet, J75, in service, after only 3 years, had achieved 3,400 hours overhaul life. And for quite a long time back now, engines have achieved 40,000 hours on wing without being removed. This was done first of all with Icelandic on an RB211 and 757, and later with Malev on a B737. And I think somebody recently, I think it was TU in Germany, with the CFM56 and the 737, got over 50,000 hours. Now that's an astonishing feat. And I have read that the average time for a CFM56 before it goes for its first shop visit is 22,000 hours. It may be even higher than that. That's an incredible level of reliability. Next slide, please. The big twins. Now, the Airbus were the first people to come up with a big twin, and it made its first flight in 1972. Then it was a short to medium range aircraft. Now, this was poo-pooed in the US. I was as polite as it could be at the Guggenheim lecture when it said there was considerable doubt in the US about large twins. They basically poured scorn on this and said, nobody but these daft Europeans would build a big twin. And then they realized maybe once the engine reliability got better, it wasn't such a bad idea after all. Next slide, please. So this started in ETOPS, extended twin overwater operations, started in 1987 with the B767 and the A310. Now, the A310 was never really designed as a long-range airplane. I remember a CASI lecture when somebody from Airbus came to give a lecture on the A310, and I remember they couldn't get their slide into the projector, and they had to use a screwdriver to push this slide in. They were so determined to show that, in fact, the A310 had a much smaller wing than the B767. And that was the reason why it didn't do very well. That Boeing had a big wing to start with, and they rapidly established increasing range. We started off with ETOPS 60 minutes, rapidly extended to 90, 180 minutes, and now we've got to the 330-minute current maximum. And that's quite incredible. When you think of it, 5.5 hours on one engine, carrying all the extra loads and whatnot that would have been carried by the other engine. Next slide, please. So Boeing, when they started to sell the 777-300ER, looking at very long range, they couldn't compete with the A340. Now that sounds ridiculous now, but the fact of the matter was that the A340 could go anywhere, and the 777-300ER was restricted by ETOPS. Boeing managed to get the FAA to raise the 180-minute limit by 15% to 207 minutes, and there wasn't a single A340 sold after that 207 minutes was brought in, because that then meant that the big twin, like the 777, could go literally anywhere in the world. Now the A380 in the later, it came into service in 2007, and it started to push the ranges up. The A340 already had this very long range. The A340 did in fact operate the Singapore to New York service non-stop for quite a few years, but eventually proved uneconomic. And the interesting thing is that both the A340-500 and the 777-300ER, designed for these very, very long ranges, they both sold about 50 aeroplanes. The 777-300ER did eventually provide the basis for the 200LR, eventually the very long range 777, only sold about 55 aeroplanes, but it did become the basis of the 777 freighter. The A380 and the 747-8 both had ranges of around 8,000 nautical miles. But the point was that once we got this 207-minute ETOPS and the big twins started to go in there, there was the decline of the large four-engine market, which was actually greatly accelerated by the pandemic, where passenger demand dropped off, and everything's gone down to smaller numbers, but the A380s and the 747s have largely disappeared. Next slide, please. The very, very long-range twins. Well, we've got the A330, the B77 still, but with the A330neo and with the A350, but now they can carry up to 400 passengers. In fact, I saw just last week that one French charter airline are going to put 440 passengers in an A350. And of course, here Canada have been putting 420 passengers in 777 for quite a few years. But you now have this 5,000 to 8,000 mile range, so you get pretty well anywhere non-stop. And the A330, the numbers I had some time ago, was down to £315 per passenger London to New York. The A380 was about 285, and the 777 about 280. So that's getting, but in the early days, nobody gave a hoot about fuel consumption. Next slide, please. So the latest twins, well, with the 787, 8, A350, 900, A330, 900, 777X in development. It is interesting, in fact, that the service delayed to 2023. In fact, for all you computer whizzes in the undergraduate program, I'd like to think of when there was last an aeroplane that arrived on time within about 3 years of when it was supposed to be. The 787 was at least 4 years late. The A380 was about 3 years late. The 777 is at least 4 years late. So all this computing doesn't necessarily get us the job done in time. Next slide. Well, this is in fact the engine that had a fan blade, the hollow fan. Those are hollow fan blades with no vibration dampers. And it lost one blade, fatigued near the root, took out half of the adjacent blade. But the point was that if the failure was contained within the containment ring, the nacelle came apart. That was a Boeing problem. But you can see on that engine, it's a twin spool engine, the massive LP turbine on that. Now that also the so-called booster stages behind the fan, Pratt kept on adding stages on that, which is a dead loss because they're getting slower and slower as you move back. And they developed that engine up to 98,000 pounds thrust, but they took it out of, I think it was into service, and they took it out of service and they stuck to about 85,000 pounds. And that was the only engine that ever had to go to cooling of the first stage of the low pressure turbines. This is the problem. You eventually get into a situation where you've gone as far as you can go and you've got to start over again. Next slide, please. So that's the Trent, which is a three spool engine. That design is basically conceptually the same as the RB211, which goes back to 1968. And they're now of this ultrafan changing the architecture to get rid of the IP turbine. They've got to add a gearbox and a massive change to the engine. But again, you see the large wide chord fan, and there's a big Kevlar containment ring round outside that. But I came back to start at Carlton. I went down to Arenda, and I actually was going around the Arenda assembly shop, and I came across something that looked like the foundation of a lighthouse. And I thought, what the heck's that? And it was in fact the containment ring for an RB211, which was solid titanium in the 1970s. And now all of these containment rings are much lighter, and they're mostly based on Kevlar. Next slide, please. Now, the geared turbofan developed by Pratt & Whitney, when they say 15 to 20% improvement in fuel efficiency, that is true, but it's based on the engines of 10 years ago. We're at a stage now where it's very, very hard to get even a couple of percent improvement on SFC. And everything you do to improve the SFC is going to affect the reliability and also the cost of the engine. But the gearboxes take a lot of power, 20 to 50 megawatts. And the ultrafan that Rolls are looking at, they've already tested the gearbox to something like 80 megawatts, which is enormous power. And although the geared turbofan has had a lot of early reliability issues, quite a few in-flight failures, the interesting thing is, I don't know any of these related to the gearbox. A lot of them have been in the low pressure turbine, again, because they went to newer materials in the LP turbine, and I think they were going to titanium alloys in the last stage. But the point was that the gearbox appears to be highly reliable. But the other thing for the young folk in the audience, the geared turbofan has a great deal of acclaim recently, and quite a lot of people think it's something new. But in fact, the first successful geared turbofan was the AIRCRAF Type 731 business jet engine, which was certified in 1972, and at least 12,000 have been built. So the geared turbofan has actually been around for almost 50 years. Next slide, please. Okay, latest single aisles. The A220, of course, was the Bombardier CS100. That's got the geared turbofan. A320neo has got a choice between the LEAP engine and the Pratt & Whitney turbofan. Now, the interesting thing is that it was claimed when the geared turbofan came out, this was a game changer. It was so much better that nothing could compete with it. The fact is, the latest numbers I've seen on the A320neo is the split is something like 60% LEAP and 40% Pratt. Just recently, one of the big American airlines, Frontier, switched from using the LEAP engine to the Pratt engine, but just before that, one of the big Indian airlines, Indigo, switched from Pratt to the LEAP engine. Maybe got that the wrong way around, but the point was there were two big swaps, and they went in opposite directions. But on the other hand, see that LEAP is also in the 737 MAX. So they've got a much bigger market than Pratt in that field. Well, next slide, please. Now, we'll go through these a bit quickly. In the 1990s, the regional market opened up and there were a lot of turboprops. The small market was shared by Pratt and Garrett, who are now Honeywell. Started off as Air Research, they're now Honeywell. And there was the PW100 and the General Electric CT7 based on the T700 turboshaft engine, military engine, shared the bigger market. But the point is that eventually that market is now only the PW100 series, PW100 and the PW150. But there were the Dash 8, the British Aerospace ATP, Embraer 120, Fokker 50, Dornier 328, and the ATR 42 and 72. Now, all of these have gone now except the ATR and the Dash 8. And the Dash 8, I'm afraid, is very nearly gone. There's only a very small backlog. And Air Canada have just announced last week that they're ditching their entire Dash 8 fleet with one of their subsidiaries. And Porter have been shut down with the Dash 8-400 for over a year. There's not anything wrong with the aeroplane, it's just the way the market's gone. But interestingly enough, 25 years ago, I had a big argument with my good friend John Thompson, who was the vice president of de Havilland, and I said, you don't need all that power in the Dash 8-400. The increase in speed is not very useful over the distances you're going to fly. And in fact, that's like the main reason why the Dash 8 has essentially failed in the market. It's a good aeroplane, but the ATR 42 and 72 suit the market much better, and that's very clear from the sales. And see, there's talk about maybe a big new turboprop engine, but I don't see where the market is, why anybody, an engine manufacturer, would go after a new turboprop at this stage. In recent years, the total sales of turboprops might have been about 120 in a year, worldwide, split between the Dash 8 and the ATR 72. And I don't see another new. GE have actually have been developing a new turboprop for some time, and what little I've seen of it looked like it was pretty much a copy of the PT6, but hasn't made any real inroads yet. So the turboprop market is very quiet. I think there is a real market for the small turboprop linking small cities. And there's just recently a lot of cities in Canada have lost their air service because Air Canada and WestJet have pulled out of the smaller cities. So something that can support a 737 or an A320 could support a Dash 8 or an ATR 72. Next slide, please. Okay, if you look at the regional jets, in fact, just last week or a couple of weeks ago, I saw that Bombardier had just delivered the last CRJ to be built. And it's rather startling, not many people realize this, that Bombardier built 1,945 CRJs. That's a huge number. Embraer built a small airplane, the 145, which was based on the little turboprop, the fuselage, with jets replacing the turboprops. And that did very well, but it's really too small an aeroplane. One of the interesting things is we recently had two aeroplanes hydroplaned and overshot the runway in Ottawa in heavy rain. And they were in fact both Embraer 145s. And one of the key things interesting about that is that's one of the few modern business commercial aircraft that doesn't have thrust reversers. Okay, next slide, please. So anyway, the 50 to 70 seat regional market is dead. And a lot of this is because of the US union airline pilots unions about how many people you can put in a regional jet, and particularly what the weight can be. So that the market is very small. Embraer have extended their market for the E175 up to the E195. They've sold a few in Europe. They're onto the same limitations, but virtually none in the States. And the Mitsubishi programs, which have been going on for years, have pretty well been cancelled. I say the Q400 backlog is only 17. Next slide, please. Well, that's just the quick look at the evolution of turbine design, and probably skip the top 4 and look at the bottom 4. And you see that we've gone from, well, the RB211, 22, 14 stages, pressure ratio of 25. Trent 700, 15 stages, pressure ratio of 36. Trent 1000, 15 stages, and the pressure ratio of 50. And the UltraFan, the pressure ratio of 60. And the bypass ratio got up 5, 10, 9.6, 15. And the cruise SFC, if you go from 1995, 0.56, 2011, 0.506, 2015, 0.48. And then it's not really a great gain for the colossal level of complexity that we're bringing in. I have heard that the takeoff turbine inlet temperature on the Trent XWB is 2000 Kelvin or higher. That's a temperature I can't believe, but it's, I mean, you're well above the melting point of the base material. So if your cooling goes wrong, you're a dead duck. Next slide, please. So you're talking about future projects. Rolls-Royce are talking this UltraFan, and they're building a demonstrator engine using a power gearbox architecture. And they say 25% reduction in fuel burn. But that 25% is relative to the Trent 700, which has been in service since 1990. And Boeing 5X, based on the new mid-market aeroplane that Boeing have been whittling away for a long time, trying to come up with an aeroplane here. That meanwhile, Airbus have sold God knows how many A321 XLRs, and Boeing are got to get off their duff very quickly to be able to compete in that market. But the fact is that we're at a stage now where it's very difficult to see somebody building a brand new engine, because we're running into a new concept where there's so much environmental pressure, particularly in Europe, that maybe a gas turbine is no longer viable in short-range markets. That's possibly where electrical propulsion may come in. I don't think electrical propulsion is going to come in on large aeroplanes. I can't see how they're going to do that unless with a gas turbine to provide the power to charge the batteries. But I think that there's a lot of work going on looking at hydrogen. Well, I came to Carleton in 1975, and at that time, the real going thing that was going to totally change the world was the hydrogen economy. That was 40, 50 years ago. And I haven't actually noticed the hydrogen economy has arrived as yet. But the hydrogen economy, I think, is a bit like the paperless office when I was first chairman way back in 75, I had a bright young lady that offered me the paperless office and I'm still waiting to see that arrive, and I've been retired for 20 years now. I think that's the last slide, Omar. Is there one more? Next slide. Yeah, the state of the industry. I say the pandemic has really caused utter chaos. If you look at Air Canada, it posted 73% decline in passengers. In fact, I thought it was more than that. Many airline bankruptcies. Say Flybe in the UK were the largest Q400 operator. Rolls-Royce downsizing 17% of its workforce. GE have done the same. Of course, the 737 MAX shaking public trust, the certification process, and concerns over climate change will drive R&D investment in technology. And we're looking at things like more electric, sustainable aviation fuels, and hydrogen. And there's all sorts of infrastructure problems associated with all of these. And so it's difficult to see somebody at the present stage starting a brand new engine of the technology we know now. And I certainly, if I was leading any major engine company, I would say this is the time to be spending and looking at baseline research to see what the problems are, and not commit to an engine just now. And airlines, of course, you can come up with a really hotshot new technology in airlines and say, don't want to know about it. We like what we've got, we're used to it, and some brand new technology, whatever it is going to be trouble. Next stage, next slide. So there's the conclusions. That the most important conclusion there really is, though, it's revolutionized the way we travel, made world travel available to mass market. When I left Glasgow to come to Canada, I thought conceivably I might make a couple of trips in a lifetime. And I've actually made about 150 Atlantic crossings. I mentioned that I got this achievement award from ISABI last year, or the year before, and I had to go to Canberra and back in a week. And I can assure you, I went business class in that, and it was a whole lot better, 14 hours from Vancouver to Brisbane in a 787, and that was a whole lot better than 14 hours across the Atlantic in a LOCKHEED Constellation. So I'll stop there and answer any questions. So we've overrun our time a little bit, but I would know where to go, so I'm okay.
Yeah.
Any questions?
Yeah. So
yeah,
thank you, Jeff. Yeah, please.
No,
please
go ahead. Go ahead, Omer.
Well, I was just going to pass the mic over to you. So yeah, please, Jeff.
Okay. Thanks very much, Herb. It's great to hear you again and hear your gentle opinions on things. I think people have enjoyed those for many years, and we're happy to again have your feedback on things and your propositions for the future. There are a few questions here so far. First one,
I see them there.
if we go back to the first one, I guess from
The
Paul
JD8D came from the J50. The JD8D came from the J52. Somebody's put that there originally in the Douglas A6. I couldn't remember. It certainly wasn't the J79. The J79 eventually became the. They put an aft fan on it. It went in the Convair 880, and it was a total disaster. It went in the Convair 880 and the Convair 990, and it was GE's entry to the market, and it was nearly their exit for good. Okay, I can't see below the
question from Paul Penna on the TF39 about the inlet cowling and the design of that to, I guess, reduce the Mach number at the face of the fan. So that was kind of an integrated design of the inlet. Could you comment on that?
When I was a young, keen professor, I used to say to answer the question that I don't know, but I'll find out. But now that I'm an old bugger, I just say, I don't know, I don't care. Sorry, Paul.
It was kind of an aerodynamicist question, though.
Yeah. Which engine did the Avroliner use? He used the ALF 502, which was also a geared fan engine developed by, originally it was a Lycoming. It was developed from the T55 turboshaft with a fan replacing the helicopter rotor. And it was also originally used in the first Canadair Challenger, and it really wasn't terribly great success.
Okay, a question, I guess the progression from 4 to 3 engines, do you see, question from Alex, do you see there ever being a single engine long haul commercial aircraft?
Not that I'll be on. I think that would never be allowed from certification point of view. Because one of the key requirements in certification is you must be able to sustain an engine failure at the critical point of takeoff. And that's rather difficult if you've only got one engine.
Right.
So, but on the other hand, having said that, there are lots of the applications with the PT6 on the Cessna Caravan, which does that on a small scale, and GE are doing something with a similar sort of bigger Cessna aircraft coming up just now. But certainly that I know that Pratt & Whitney had quite a lot of trouble getting certification rights on the PT6 as a single-engined civil aircraft. That's only about a 10-passenger aircraft, but certainly not for a big engine. In fact, interestingly enough, when I did this lecture in 2000, I sort of said, well, what's the projected growth of engines? What will the Guggenheim lecture 20 years later say? And I said, I don't think it'd be anything more than about 135,000 pounds thrust. And I'm sure that's already too high, because we now find that the thrust requirement for the latest version of the 777 is in fact less than the previous version, because having gone to a composite wing, the aircraft weight is significantly lower. And the next aircraft that will follow that will have a composite fuselage as well. So I think that we're actually at the point of the biggest engines we're likely to see right now. We may see slightly higher fan diameters, but the thrust levels will probably be less.
Okay. The comment from Adrian, I guess, on your comment about the -8s being retired, commenting that it was the 300s that were being retired from Jazz, that he thinks the 400s will still be around for the foreseeable future.
Well, yes, I hope so. But in fact, that's precisely what Flybe gave up on. Flybe were the biggest operator of the 400, and they withdrew it. Yes, you're quite right. It was the 300s that are leaving Jazz, but the 400s, in fact, never sold as well as the 300. And the 400s will probably keep going for another 15 years, 20 years, but I don't think any more will be, very many more will be sold.
Yeah, it will be interesting, as you said, to see if when air travel starts coming back, whether the turboprops come in to service the smaller cities that have had their jet service canceled.
Yes, well, I mean, the point is that if they were having a sort of odd visits from a 737 or an A320, that the turboprop, small turboprop, is much more viable for that.
Okay, here's a question from Stefano. How viable do you think short-haul commuter aircraft would be, like the development at Viking Air of the DHC-2 and possible Twin Otter going to be?
Oh, I think there's a small market, small continuing market for that. That will go on for a long time. Now, when de Havilland built the Twin Otter, they never expected to sell 800, nearly 900 aeroplanes on that, and that certainly that there's a small market all around the world for small seaplanes, and that will certainly go on. There was a question before that about also Dick Kane. How does the power gearbox architecture alter from the Pratt & Whitney geared turbofan architecture? The basic difference that I know is that one of them, and I can't remember which one it is, I think the Pratt, when the planets are fixed and the ring gear revolves around that, and in the Rolls-Royce it's the other way around. Maybe Omer can answer that question, but that's the definite basic difference between these two. One of them, the ring gear is fixed and the planets rotate around in that, and the other one, the planets are fixed and the ring gear, the planets are fixed and the ring gear rotates around that. And that I think that the Rolls-Royce has a higher gear ratio.
Okay. Todd, I just want to ask, how much time do we have left? Do we have a time limitation with the event?
We can go for 23 and a half more hours.
Okay, all right.
Hello, this is Ben Tahir. Can you hear me?
Yes.
Yes.
Yeah, Professor, I'm going to your alma mater, University of Glasgow. They have accepted me for an MPhil. And,
Good for you.
well, thank you very much. You remember me, you met me the last meeting we had in 2019.
Yes.
Anyway,
Yes. Yes.
I'm wondering, since you're an alumnus, can you give me some kind of a note to take with me when I go there? Because right now everything is closed there. The university is not what you call it, is under lockdown.
Yes. It's the same at Carleton. I'll just take enough whiskey with you that would make life easier.
You have an email address I can write to you?
Yes, certainly. hihsaravan@gmail.ca.
Can you please
Just the
repeat?
first-
I'm deaf. Can you please repeat?
HIH.
We will put you in touch with each
Yeah.
other on the back end.
All right. Thank
Yeah.
you so much.
You're
Oh,
welcome.
you're welcome. And there was a question from Stefan's. Somebody from, sorry. Thank you. What was the most surprising breakthrough in propulsion to you? In other words, was there any breakthrough that changed the industry in a more positive way than you had expected? And that's a question. No, nothing really sensational. There's a difference has come along. It's been a steady increase in cycle conditions, in reducing the number of stages, and stuff like that. I was asked a similar question in Australia when I gave a paper on turboprops 30 odd years ago. And what did I expect to see at the turn of the century? And I said the same as what we have now, but somewhat better. And that everybody said, "Oh, that's ridiculous." And in fact, it was absolutely right. And basically, there were several big steps. The really big step change that made the real difference was the high bypass ratio engine. And that required the aerodynamics applied to the fan, the better structural analysis of the fan, better manufacturing methods and so on. And that was something that was really a very, very big change. And as I say, that the geared fan, which is coming in now, which many people think is a big change. We've had geared fans around for a long time. I say going back to the Garrett 731 and the 4-engine British Aerospace. Forget what they call it. It eventually became the Avrojet. But the geared fans have been around for a long time, and we're just now going to higher powered fans. I was always very skeptical about the high powered gearbox, of how you could get rid of the heat in the gearbox, but that doesn't seem to be a problem. I hope they're right. It's interesting because at one stage I went over on a visit to Rolls-Royce. I was at the time of doing the 6th edition of my book, and I had lunch with the president of Rolls-Royce. What he wanted to know was, what did I think about gearboxes? And I was kind of flattered that Rolls-Royce would think that my opinion on gearboxes would be of any use. But I said then that I thought that there was a limit to how high you could go in power on a gearbox. I've done a lot of work in industrial gas turbines as well. And in fact, that I remember doing a job for Atomic Energy when they're looking at a gas turbine for use with a reactor. And I started looking around for what was the highest power in a gearbox for anything. And that like a gas turbine. And I found that nobody had built a gas turbine gearbox of more than 80 megawatts, even for the biggest single shaft gas turbines. they have now, but most of the really big gas turbines don't have a gearbox to drive the generator directly, so that we hope that the big gearbox that Rolls are going for will be as reliable as the one that Pratt have done, but certainly that I think they're doing it very sensibly. They're doing it bit by bit, and they're not going to commit to a final engine for quite a long time. But so I'd say that it's just been a case of steady development. They're going to higher temperatures are more and more unbelievable, higher pressure ratios, higher rotational speeds. And for example, the high pressure spool on the RB211 ran at about 10,000 RPM. The high pressure spool on the later Trents run at 12,000 RPM. So that's a 44% increase in centrifugal stress there to start with. And you push the turbine temperature up probably 300 degrees centigrade. So that, you know, everything's really running. I used to sort of say that a good engine was running just on the point of braking, or it was too heavy. And that's not too far from the truth. So that you've got to be careful when you say, let's push this a bit further, push it a bit further, and then you're surprised when it breaks. As I say, I think the gas turbine, as we know it, has reached a plateau. That, you know, it's going to be very. If you say for example, you want to go up from a pressure ratio of 50 to a pressure ratio of 60, that makes your high pressure compressor blades extremely small, and it becomes very difficult to maintain the same level of tip clearance to the length of the blade that you had at a pressure ratio of 30:1. So that you might well find that when you push the pressure ratio of these compressors up too high, all of a sudden you've lost efficiency. So that you may in fact have been better, rather than going to a pressure ratio of 60, to have gone to a pressure ratio of 55. Who knows? But all I'm saying is that that when you keep pushing the technology harder and harder and harder, eventually you come to a limit where you can't do any better. And we're actually quite close to that now. Any other questions?
Yeah, good. There's one from Ed here saying whether, I guess it's the shorter term question of having aircraft sitting around for a year on safety, but any other changes you think are going to result from this year of the airline sitting on the ground?
Well, I've asked about that question myself. That I remember not too long after I came to Carleton, it was not too long after the LOCKHEED 1011 came out, that Air Canada had a 3-week strike, and the first L1011 out of Montreal going to Calgary landed in Ottawa, having lost all its lubricating oil. And that was because the heavy rotors had sat on the same point for 3 weeks, supported by knife edge seals, and they distorted these, opened up the clearances, and literally between Montreal and Ottawa, all the lubricating oil in the engines had leaked out through the seals. Now, I wrote to a guy, a man called Bjorn Fern, who works for Liam Industries, who's very much, in my opinion, an expert, and asked him this very question. And he said that basically all of these engines that, all of these aircraft that are stored, would expect the aircraft to come back into service. They run the engines once a week and check them out. So not actually, if you left them for 6 months without running, I would certainly expect to have all sorts of troubles. Now, one of the things that did amaze me more recently was that a few years ago, I forget what it was, at some air show over in Hull, the Classic Wings, whatever they call themselves, they actually, Chris Hadfield, the astronaut, actually flew a Sabre with a 50-year-old Orenda that had not run for the last 50 years. And I thought, that's impossible, you can't do that. but somehow they got it overhauled and ran, and he actually flew this 50-year-old aeroplane with a 50-year-old engine that had literally not run for 50 years, which I thought was absolutely astonishing. And I don't know where they found the people from Orenda that knew anything about the engine after all these years. But certainly that a lot of these aeroplanes that are in storage now will never fly again. And I'm sure that the 777s that have the PW 4000 112-inch fan engine that need all the fan blades rechecked and whatnot, I'm sure they'll not fly again because they were already towards the end of their life. So that it depends on the aircraft life when it goes into storage and whether it's worth bringing it back to service. But certainly you have to be very careful doing that.
Yeah, I think there was a story about Southwest actually cycling their whole fleet through actual air operations. They weren't mothballing or pickling anything. They were flying them a few days a week so that they could keep all of them running. Well,
quite a lot of airlines have been doing that with a few airplanes, and one of the reasons for doing that is to keep the pilots current. That the pilots haven't flown for 6 months, they've got to requalify. I don't know what the times are, but of course the point is if you put 60 or 70 aeroplanes in storage, it's quite a big job to move. If you look at the way all these aeroplanes are parked in their hundreds, it's obviously quite difficult to sort of move them around, and so that I think that a lot of these will in fact not come back to service. I think I did read recently that absolutely staggered me was that they're claiming now that a lot of aeroplanes, 95% of them can be actually recycled. I find that absolutely astonishing. I mean, there are some parts that you could probably use again in another aeroplane, but apparently virtually everything in the aeroplane, less 5 or 10%, can actually be recycled and used again.
Good, thanks. Looking down further. Any comments on the hydrogen powered -8 300 conversion being proposed?
I didn't even know about that.
Okay.
Those of you who are interested in hydrogen conversion, if you look up Leham News, Leeham News, and look at the man called Bjorn, Bjorn, Ferm, Fehrm. He's a Swedish former fighter pilot, and he does a lot of technical work for Leham News. And he's done quite a considerable series recently on the problems of putting hydrogen in aircraft, particularly where you can put the tanks and what the fire hazards are, and things like that. So I don't see myself what would be the advantage in putting hydrogen in a -8 300. I'm sure it could be done, but I can't see that it's economically viable myself, and that I don't know how many you'd be able to convert and how many people would buy it, and I would not put my eggs in that basket. I hadn't heard of this at all. I don't want to be a negative Nelly, but I've actually had a fairly long track record of getting some of these forecasts right. But.
Yeah, so if Adrian's still there, if he wants to post a further question or clarify that on the chat. There's a question from James, which I guess extends and looks at your idea of adaptability. Is there a developing future for small and micro gas turbines in unmanned aerospace or distributed power generation? So it's getting to back to your industrial roots.
Yeah, well, I'm not really. I looked at small gas turbines a long time ago, and I expected to have seen more small gas turbines used. But the point is, you can't really make an efficient small gas turbine, period. One of the things that gas turbines can be used for, where efficiency doesn't matter so much, is for burning off flare gas. You know, if you've actually got flare gas which you'd like to get rid of, you can run it through a gas turbine and get 30 kilowatts or 50 kilowatts, and that's a good use of that. But again, about 20 years ago, there was a great push towards the micro gas turbines and whatnot, but that hasn't really come to a lot. And there's one outfit, the name, not Centrax, it begins with a C, who do make small gas turbines around about 500 kilowatts or thereabouts, but they've not sold really an awful lot of these. So I think that actually the gas turbine the industrial gas turbine is going through a difficult time, because we've now come to a point where an area where the gas turbine was quite dominant, around about 15 to 20 megawatts, the diesel has suddenly become competitive there. And that was an area that the gas turbine had the market pretty well sewn up, and now the diesel is getting in there. And the sale of very big gas turbines has really slowed down, and the GE have lost tons of money. Alstom have dropped out. Siemens have cut back their operation very significantly. The industrial gas turbine is going through a very hard time just now. In a lot of electrical applications, one of the problems with the gas turbine is that very often that you have to, by law, bring on the renewable stuff first. And then when the wind stops blowing, the gas turbine has to jump in and immediately come up to power and save the day. And of course, this is very, very bad from the point of view of maintenance, but there's nothing worse for a gas turbine than fast starts. Now, to put that in perspective, the Rolls-Royce Avon, which was very widely used in Canada and the pipeline business, and it was also used in Europe more than here for electrical power generation. TransCanada Pipelines operated the Avon with an overhaul lives of up to 30,000 hours. And they could have gone more than that, but they did a long study of that and came to the conclusion that you were certainly losing power all the time out to 30,000 hours, even though you couldn't measure it. And it was actually best to do an overhaul and maybe something like 25,000 to 27,000 hours, which was a cheaper overhaul and would in fact be more economic. Now, the Central Electricity Generating Board in Great Britain, using the identical engine, achieved an overhaul life of 500 hours. And that's quite a difference, 500 hours for one engine, one application, and 30,000 for another. And the reason was that all of the CEGB starts were black start to 100% power in 120 seconds. So in fact, and their average running time per start was 14 minutes. TransCanada Pipeline, their average running time per start might have been as high as 3,000 hours. So it depends on how you use an engine. That applies to aero engines as well. The difference between fighter engines and bomber engines or long haul transport engines. But I don't really see, I've looked at this for quite a long time, and I think that the microgas turbines are not going to make a huge difference. There'll be some small applications. And I think if you look at the very small aircraft like air taxis and things like that, the gas turbine is not competitive in that size range. It's just a matter of size and rotational speed, and that if you went down to these very small units, you might be having to run gas turbines at 250,000 RPM, something like that. And you might have to gear that down to something else. Any other questions?
Thanks. I maybe two more, try and wind up, maybe one looking back and one looking forward. So Nicole is asking, of all the projects you worked on over the years, is there one that stands out?
Yes, the Olympus 593. It's incredible to believe that we designed and built an engine that cruised continuously at Mach 2, and I finished my PhD on that 54 years ago. It's rather a long time ago, isn't it? And in fact, when I think about it, after the Arrow crash in 1959, would you believe I actually worked on hypersonic ramjets in 1959, and they still haven't appeared. So that was in the past. In the future, I don't see I could do anything that would be better than what's going on now. That I think we've reached a mind-boggling level of achievement. To get much better is very, very difficult.
So can we conclude then on maybe some advice for the students that are here, and the fact that they still need to know thermodynamics? They're still going to need to buy version 12 or 14 or of your textbook, but you know, just some encouragement for what the need for still understanding the fundamentals, and maybe the idea of reliability.
Well, one of the things that's worth knowing is to look at all lectures like this, look at what's been done in the past. It's amazing how sometimes something that was a lousy idea 20 years ago pops up again, and lo and behold, it's still a lousy idea. They might have more exotic calculations to go with it now, but it's no better than it was 20 years ago. So I think that really looking back at some of the disasters that have happened and how people thought things were easy and they weren't is quite a good thing to do. I'll tell you, for example, when we built 4,000 Orenda jet engines for the Sabre and the Sabre and the CF100, and they decided to do an industrial version of this. And okay, we'll take the aerodynamics of the Orenda. We'll bring this rotational speed down 3%. That will change the stress level in the turbine by about 6%, but it'll also bring the turbine temperature down about 100 degrees centigrade. So we worked on that, and we designed a turbine, and we thought, right, that's very, very low stress. We should get 100,000 hours life from this turbine. And we delivered the first turbine to Trans-Canada Pipeline. Would you believe it shed a turbine blade after 25 hours? That was a bit short of 100,000 hours. But I remember that very well, because I was the lucky winner of the Easter weekend of 1962 to lead a little group to redesign that turbine over the weekend, so that we could tell Trans-Canada on Monday or on Tuesday how we'd fixed it. So sometimes it's useful to, it's very important to understand. This is the one thing I'd say. Today, with the wonderful computers we have and the computing, it's too easy to actually run off an awful lot of numbers and plot graphs and whatnot without really understanding the underlying physics of what happens if you open a nozzle. Does the pressure go up or down? Something obvious like that. Because actually, nobody now knows what an analog computer is. But I used analog computers for the work I was doing on engine transients, because in the days when we were doing transient performance in the Olympus 593, I had a PhD student using the University of Bristol mainframe computer, where I could do this 5-second acceleration in real time on the analog computer with a university type mainframe computer. This 5-second acceleration took 27 minutes. But the point was, with the analog computer, you could actually observe what the engine was doing when you made a change in fuel flow or changed the nozzle setting and whatnot. And I found very quickly that with this model, physical model, where I could actually fiddle with things, see what happened, I had a much better physical understanding of how the Olympus 593 operated than anybody at Bristol who'd been running this engine for 15 years. Because it was just that I had a model that could actually give you the insight into this, and it was an analog model. The digital model are nowhere near as good for looking at things like that. So sometimes you've really got to go back to very simple first principles and think in the terms of fluid dynamics, fluid mechanics and whatnot. What happens if I sort of bleed some flow off here and the flow going through the back drops? What happens then? And a lot of these things are actually easily understood and interpreted from first principles. But nowadays, with the power of computing, it's too easy to sort of run off graphs in all directions and hundreds of numbers and whatnot, and not really understand what's going on. When I went to a render, I started as a stress engineer, and there was one senior stress engineer there who could explain in absolute clarity the distribution of stress in a turbine disc or a blade without any calculations. And that is the kind of thing that has been lost, and that old guys like me, somebody could come up with a result and they say, well, that's wrong. And they say, but you didn't even check it. I say, I know, but I know it's wrong. And I remember the first thing that happened to me as a young engineer, there was an old guy with a lot of experience, and I'd done all these clever calculations, but I'd done something wrong, and that he was right. And so that really comes from having a physical understanding of what's going on rather than just ability to calculate and crunch out lots of numbers. Now, you need to be able to crunch out all these numbers, but you really got to understand what they mean. Did that sound convincing?
Yeah. Yeah, I think that's an important comment for people to take away. I note that even in this world of AI, where apparently neural networks can solve things and understand everything, that it's been now backtracking to say there's a whole new area of explainable AI, because you still have to be able to explain the answer to somebody. So that's kind of what you're saying.
Well, I'll tell you another interesting thing, that when I produced my dynamic model of Olympus 593, the British Aircraft Corporation heard what I was doing. I was doing this for Bristol Siddeley, and they heard what I was doing, and they came to me and said, can we use your model to design a new air intake control system on Concorde? Concorde at that stage had an analog system that really wasn't flexible enough, and they wanted to be able to change the control laws and the ramp angles and whatnot as the flight testing proceeded. So I said, yeah, sure, I'll come and do that with you. So they rented me as a consultant for a bit. And a whole group of these really high pressure, very bright guys set up my model on their big hybrid computer. And they phoned me up and said, well, we've got it. There was about 20 or 30 of them doing this. And they finally got this thing ready to go. And they phoned me up and said, we're going to run it tomorrow. We'll let you know how it goes. So I thought, oh, good. So they phoned up the next morning and they said, your results are all wrong. Well, that was a heart stopper, let me tell you. I thought I was going to have to put PhD asterisk results invalid. And it took the better part of a day for my blood pressure to come down to a reasonable level. And they said that you say that when you do an acceleration, the low pressure compressor working line runs along the equilibrium running line, and it doesn't, it runs right into surge. And oh my God. I thought, wait a minute. I ran this engine at Farnborough, and it ran exactly as my computer said it would. So that there's nothing wrong with my model, they've got it wrong. Anyway, it took about a day or so thinking through this and went back through my reference list and whatnot. And finally the penny dropped, and I phoned them up and I said, I think I know what the problem is. And they said, what's that? I said, you left G out of the moment of inertia. Oh, couldn't be that possibly. Then they phoned up a little bit later in the day, very apologetic, said, yes, you're right. So here you had a group of very bright people, a whole pile of them, and they got this schoolboy howler in the very first line pretty well, and then came back and told me my PhD was a load of rubbish. So that was a fairly startling experience.
Okay, well, very interesting, and thank you for that advice. I would echo a number of comments. We'll pass them on to you, Herb, of greetings from past students and former colleagues. And thank you for your time and your contribution tonight, and obviously back over many years. The legacy of your teaching and your analysis and your philosophy will continue on in many of us. And so we really appreciate that. And CASI is a great place to show the importance of Canadian engineering contributions, and the fact that people here and in CASI are committed to kind of the art and the science and the business of engineering and aerospace in Canada. So thank you very much.
Perhaps just one last thing I could say, that my older colleagues and students from long past probably don't recognize me because I used to have black hair, and just a couple of weeks ago I had cataract surgery and had worn glasses since I was 9 years old, and all of a sudden at the age of 88 I find you don't need glasses, and that's why they might not recognize me.
Well, it's a continuous improvement, right? So thank you very much. And on behalf of everybody else, I don't know that you can hear the standing ovation from where you are, but we really appreciate your time and taking so many questions tonight. Thanks.
Well, I'm always glad to do it. And anytime I enjoy doing it, I'd much rather do it to a large crowd live, but I've enjoyed doing it from here. And I hope it's been of some value to the younger students. So thanks a lot then.
Thank you. And that they will be available as a podcast so people can watch it again and pass it on to their friends. So we hope everybody will do that. Keep an eye on your email for CASI members for events in March and April in the Ottawa branch. And thanks again for your participation, and everybody stay well, and look forward to everybody getting a vaccine soon. Take care.
Thank you.
Cheers.
Cheers then.